Hi, my name is Randal Koene. I'm a computational neuroscientist, and I work in the field of whole brain emulation. That is the science that aims to achieve what is called mind uploading in the sci-fi terminology. And I'm working on that with our nonprofit organization, the Carbon Copies Foundation. Well, I should first of all say that talking about the pillars of ethical AI isn't the normal topic for me because I work in a slightly adjacent field. But I think that the pillars of it are that everyone should have the ability to benefit equally from the things that AI makes possible, and that nobody, or as few people as possible and as little ways as possible, should be in any way harmed by the development of artificial intelligence. So this is a matter of equal access and equal rights, and also taking care in development, deployment, and application. I think that it's quite important that there is a lot of open discussion. I think that to have beneficial development of AGI and beneficial AGI as an outcome, there needs to be an equal playing field where scientists all across the world have access to much the same information, are often communicating with one another, that there's insight into the kind of code that is being produced, the sort of devices that are being produced, and most of all, that there is a sort of universal agreement on what things are ethically acceptable and not acceptable. The three biggest ethical considerations. Let's see. I think one of the biggest is currently still equal access, because it's a very expensive field to be working in. So you'll see that the companies with the greatest funds available have the biggest advantage in, for example, purchasing GPUs that are currently in limited supply. And so this means that there isn't an equal playing field because of that. So the equal access question is certainly at the top of the list. Then right below that is data and who does what with data, so the ownership of data. And then below that, or maybe not below that, but the other third item, maybe they're all equally important, is that that the way that people are impacted by AI isn't something that is openly discussed with the people who are affected by it at the moment. It's mostly just something that happens where, you know, a new technology comes out and suddenly your creative endeavors are being reused by an AI that mixes them up in another way. And you had an idea this was going to happen, and you didn't know that when you were putting your work out there. Okay, so this is really a question about a situation now and a situation after AGI occurs, or human-level AGI is achieved. I think the way in which it's achieved and how all these ethical questions that we talked about before are going to be affected depends a lot on how the structure of say, economical or political and social effects on AI, how that's currently set up. Because, for example, it will determine whether or not, say, AI is developed in a closed form by, say, a commercial company somewhere, or by a government that perhaps has a very closed aspect about it. Say, maybe the Chinese government decides to do it in some way that doesn't give everyone equal access to it. So I think that matters a lot in the development of it. And now the thing is that how it's developed and what happens then in the coming about of human-level AGI, that's going to impact what happens afterwards, because it's quite likely that if you have a superintelligence developed by someone with a certain perspective on all of these matters, then that may be accentuated and focused even more after the development of that AI happens. So you may find that whatever the situation is before becomes even more strongly that situation after, whereas perhaps what we're hoping for is that, you know, development of AGI would lead to in an era of abundance, a time when maybe because AI can do so many good things for us and will come up with great decisions, very smart, rational, awesome decisions for things in the world and do better in medicine and all of those things, that it will simply be, helpful for everyone and give people more wealth and have less work to do and all of that. But I think the risk is that it's the perspective on how the world should be of those who develop it that will become part of how AI behaves and how we use AI afterwards. So you see that accentuation. Mind uploading is the process of taking a person's mind, so a patient's mind, a very specific individual's mind, that which the brain produces, and being able to somehow transfer that into some device, code, whatever you want, that is able to continue that mind, so that that mind continues with consciousness, feelings, and so forth, as it was before, but not in that same organic brain. So another way to look at it would be, say, a full brain prosthetic, if you want, or a full body prosthetic, if you look at it another way. Oh, I got interested in it a long time ago, probably when I was around 13 years old or so. It came about from a number of different angles. One was that I was just interested in figuring out any kind of way of solving many problems at the same time, where all the problems that I kept bumping into was how many different interesting, cool things can a person do? What are we even able to do? What aren't we able to do? All those things just kind of kept amounting to one major problem, which is, oh yes, we're limited in what we can do because of our minds, how our minds work, how our brains work, and how our brains are embodied and so forth. So there's this natural limit. And then on top of that, just this notion, because my dad was a physicist, that everything is basically just what we're seeing around us, matter, energy, various fields, that there's really no distinction there when it comes to what creates a mind, what creates humans. We must also be part of this physical universe. And so why wouldn't you be able to do the same sort of thing in another substrate? Why wouldn't you be able to put that in another device and be able to continue? I mean, we can build replacements for all sorts of stuff. Why can you not do that for the brain? And that eventually evolved into working in computational neuroscience. That's that second part, whether or not a substrate-independent mind is philosophical or scientific. Well, something is scientific if you can test it. So if you can make a hypothesis that you can test, right? Now, a substrate-independent mind would be a mind that can run in other substrates. It does not mean a mind that has no substrate. That's very important to make that clear. We're not talking about a mind without a substrate, just that the substrate can be changed. We could call it a platform instead of a substrate. It's like changing the platform, the type of computer that some code runs on. So the question is, can you do that with a mind? Is that, like this can you do that? If you were to ask that or ask hypotheses about that, how would you do it? Can you make substantive scientific progress on that? And I believe that we have gotten quite a bit further towards that goal already, so that many of the questions around substrate-independent minds have become testable. So for example, we can start doing things like moving what is going on in the brain of a very small animal or of some cultured neural tissue and try to move that into a computer by building models that do the same thing based on very detailed analysis of that brain tissue. And then you can explore the behavior and you can test, is the behavior the same? Are the signals that you can see in this virtual brain, are they the same as what you would find in the original tissue? You can do those kinds of tests. So in that sense, this is very scientific. It's a scientifically testable set of procedures and questions. The philosophical questions that are still attached to that are about things like personal identity and consciousness. Now, I don't think that there's any real reason to believe that consciousness is ultimately somehow uniquely or vastly different than all of the other cognitive things that are going on in our mind. All of those are based on emergent things that are coming from the structure of the brain and the function of the brain. And I think that the same thing is true for consciousness. The question of personal identity as a philosophical question of, who am I, what am I, does personal identity even exist as such? Is it possible for personal identity, for being, to be, say, on at one moment, off at another, on again at another? Is there such a thing as, say, a stream of consciousness? These questions are still largely philosophical, but I believe that those also are testable. Some of them are testable in the sense that we can make judgments about them based on how we judge consciousness and personal identity now. So, for example, if someone were put into, where their body temperature were cooled down in a hypothermic procedure so that you can do heart surgery on them for an hour by cooling them down to the point where there's very little going on in the body, it's possible to work on them much longer without brain damage. In this procedure, all of the activity in the brain ceases. Well, if this person has been under that procedure and they come back, you don't suddenly sell their house or tell their spouse that they're not married to them anymore because it's not the same person. So obviously we assume that if someone has been basically off for a while and then on again, that they are the same person, which just leaves the question of what about the change in material? And we know, of course, that the atoms in our bodies change over time and molecules change and neurons can die and others can appear and we stay the same. So then there are questions about, does there need to be some kind of continuity to it? And that's when you start getting into the truly philosophical questions, like the ones that Derek Parfit asks about, what if you suddenly recreated someone through some lightning flash somewhere, and if they had all the same molecules and atoms as the original person, would that be that person? And at that point, well, I mean, that to me is a philosophical question and not a scientific one. I don't know of a way to test that, because all you can do is ask someone, hey, are you so-and-so? Do you feel like that person? Is this you? And then they'll say yes if they believe it, and maybe if they don't believe it, they might say no, even if they are. I mean, how would they even know? It's very hard to test that. So I guess it was a mixed answer. Some of these are scientific questions, and some of them are possibly going to be philosophical ones forever. Okay, let me start by saying that there probably are a lot of things that we don't yet know about the brain that would be very relevant to AI, because the chances that in this vast 86 billion neurons, trillions of synapses network, that there isn't something there in terms of the circuitry that is really crucial to certain cognitive actions, that the chance that there isn't something there, that we've already found it all, is extremely slim, I would say. So that, first of all, just as a blanket statement. Now, there are some specific things that I think are important. First of all, I'd like to set aside the real complexity in terms of all the different neurons and different types of synapses and ion channels. That's important in the sense that you need to have lots of good messengers that can carry around messages of certain types and will only connect with destination locations of some type. That's very interesting and useful, but you can come up with alternatives for that in electronics and in computer code very easily by just giving something a certain type. Not a problem. I think the more important things that we already know that are different in the human brain than in artificial neural networks is, for example, the number of different processes, the number of different stages that it takes to get a certain thing done. Take memory, for example. In memory, when you look at what happens in, say, large language models or in many other, deep learning, etc. models right now, you typically have one way of learning. There's one learning algorithm, and that learning algorithm is applied to all the data that's fed in, and then that algorithm determines what types of structures are set up in that neural network, and that is then what you've got. In a human brain, that's not how it works. We have information coming at us all day long, and it goes through a whole bunch of different filters. It goes through filters at every stage. So some things we'll pick up on, other things we won't, and it depends, for example, on where we tune our attention to, where we turn that to, what's going to be picked up. But also many other things, like, for example, if we remember something, is something going to come up tomorrow that is similar? So will it cue that thing that we just remembered and make it reactivate so that it will become a stronger memory instead of just dissipating after a while? And so as part of that, in the human brain, you've got short-term memory after these sensory filters. You've got an intermediate type of memory. The short-term memory is just sort of an activity buffer, and it can grab something in an instant. You need to be shown something only once, not 1,000 examples, as you might have to do with, say, images that you're feeding into a computer, but just once, and you can repeat that in your mind for a while. Then you have intermediate-term memory that is based on this molecular process called long-term potentiation and long-term depression, LTP and LTD, and that is able to lock in a memory for a little while, but only with the help of certain parts of the brain, like the hippocampus. And that's an area that you could see is like pointers that are pointing at other parts of the brain, say audio, visual, and so forth, and is grabbing onto activity patterns that are there and combining them. So there's an integration going on across different sensory modalities. And then over time, that gets embedded in synaptic change. So you have long-term memory. So first of all, you've got this whole sort of this progression through different temporal levels of memory, and at each level you've got filters in place. Then over long term, you've got this reactivation, and so you've got kind of an interleaving of things you've learned at different times that are associated with one another. So you eventually have some things that are very important to you that you can retrieve in many different ways by various kinds of cues. And there, in addition to this temporal aspect, there's also sort of a distribution in types of memory. You've got procedural memory, and you've got episodic memory, so memory for different types of things that you need to remember, whether it's more about an activity that you're doing or whether it's an event that happened. And on top of that, again, you have not just this kind of memory that is creating your intelligence, but you also have processes such as, in our prefrontal cortex, the ability to do this reinforcement learning and a kind of planning and running different plans at the same time subconsciously and finding a solution. So you've got all these different systems working together. And that's really, to me, the biggest difference between what's going on in the brain and what I see in most types of AI, because most AI that we see today is of a single kind. It does a single thing, has a single algorithm. And when I say single, okay, sure, has lots of lines of code, but it's one principle that's being embedded there. And the brain is a whole collection of different things. And so you'll see, for instance, at this conference that many of the AGI approaches here are different from what you might find in an LLM, in that they also look at it as being a collection of different things that you have to put together. So I really appreciate that about the approaches that have been taken, for example, the ones that Ben Goertzel goes after. Yeah, so this question about backpropagation versus other ways of learning, this connects to my previous point. And first of all, there is actually a chance that backpropagation as such also happens in the brain. Because in neurons, neurons have an axon, that is the output side of the neuron, and they have dendrites, those are the inputs to the neuron. It's not that the activity only travels up the axon and out towards its other targets, but when an action potential happens, there's also a backflow of activity into the dendrites. And there are a number of papers out now that show that there is actually an effect of that backpropagated activity on the ability to strengthen synapses. So the backpropagation of that activity and the forward propagation from other neurons, they combine to make the strengthening of synapses possible, to make LTP possible. So there's definitely an opportunity there for a biological version of what backpropagation really is. But that said, the evidence is stronger and still much more pronounced as a very classical thing that to have Hebbian learning in the brain, which is basically this notion that two things that fire together wire together. If two neurons are active at the same time and there is a connection between them, that connection will be strengthened. If they're not active at the same time, then perhaps that gets weakened. Let's say if A fires before B, then a connection from A to B would be strengthened, but a connection from B to A would be weakened because it's in the opposite order. This is also called spike timing dependent potentiation. And that principle works fine for creating patterns of neurons. And as long as what you need to establish, let's say, a neural program of some kind is just to create useful patterns, you can use that. In some contexts, that is not as quick, it's not as efficient as the gradient descent that you get with backpropagation, which is why the ability to do backpropagation in biological neurons is actually very interesting. But yeah, you could also do it in other ways. And there are sort of macroscopic principles that also come to bear, such as this, the importance of attention and therefore the upregulation of neurons that are more ready to be moderated, to have their synapses change at a certain time because there is an influx of activity from elsewhere. That's the attention influx there, giving it a greater ability to fire. Well, we have a very hard time with abstract knowledge. It's not something that's as natural to us as recognizing a bicycle or a car. We certainly don't do these things quickly. That's why, you know, if you have a mathematician sitting there carrying out calculations, that's considered quite an achievement, or a philosopher thinking through something. So logic and abstract thought is not something that comes very naturally to the way neurons in the brain work. So what I'm assuming, just from, you know, it's definitely not my area of expertise, but I'm assuming that the way that is implemented is a kind of symbolic architecture. It's sort of a neural version of what a symbolic AI architecture might be, so that you have representations of neurons that can form a representation of a certain type of symbol that you might use in a mathematical equation, and that you would have a process that you would apply to knowing how to do, say, carry out a multiplication, that you can then run that symbol through, which shows why it would be very difficult to do, because you would have to hold variables, you'd have to hold some of these results temporarily in short-term memory, and our short-term memory is limited. And of course, if you write things down on paper, that helps a bit, but it's still very difficult to do mathematical equations in your head for that simple reason. So the encoding of symbolic knowledge, not sure it's specifically just about that. The hippocampus has this particular feature that, because it acts like a set of reusable pointers, the neurons in there, they don't always represent the same things. They're temporarily used to represent connections between different patterns of activity that happen in the different cortical areas of the brain. So for example, the visual area, or the language area, or some other processing area, there will be a pattern of activity, and the cells in the hippocampus that activate at the same time as that activity become connected to that. They create a stronger connection. And so from then on, you can reactivate those few cells in the hippocampus that now represent all that activity in some area of the brain, and it will reactivate that. So if you saw a car, you have a cell in the hippocampus that activates, that then recreates again that activity that says this is a car. Now, if you saw that car drive through a red light, you had another representation of the red light and a screeching sound from another part of the brain, and the hippocampus can record these episodes. So it has these pointers saying this, then that, then that, then that. You've got these episodes of memory. And those episodic pieces of memory, that's what you can use to carry out something procedural. Like, for example, if you're wanting to do mathematics, you want to do equations, then you need to know how to carry out a procedure. So you have to be able to record a procedure like that first, learn it, and then after a while, if it's been done many times over, if this is reactivated during sleep in the hippocampus and reactivated in the cortex, then you get connections in the cortex that will hold those episodes so that it's no longer hippocampal dependent. And that's what you see if someone's hippocampus is damaged. Older episodic memories that have been already encoded in the brain that way, they remain, but you can't make any new episodic memories if your hippocampus has been damaged. But the hippocampus is essential for this process of new episodic things. So you would have to use that if you're working on, say, a difficult symbolic process. You want to be able to remember that you just thought about that, and then that, and then that, and you want to combine them in some way. You want to carry out a process on that. You need a place where you can do this, and the hippocampus with a bunch of pointers is able to do that. So I had mentioned that my main goal is whole brain emulation for mind uploading, right? And to do whole brain emulation, to emulate an entire brain, what you need is a way to capture all of the essential data that you need from the brain, and then you need to be able to build a model. Now, capturing all of the necessary data from a brain by recording activity in the brain is not currently possible because there is no method that can capture activity at the resolution and at the scale that's necessary all at once. We have things like calcium imaging and electrode recordings. Those don't do the job. They're not good enough for that. So what you need to do instead is use a technology that we do have access to, which is electron microscopy and a few other microscopy methods that can capture the structure of the brain in great detail. That means you look at a sample of the brain and you just go through many layers of that sample, and you obtain images that give you a really high resolution details of every neuron that's there, so that you can look at them, you can see their structure in terms of dendrites and axons and synapses. You can even see the little vesicles that carry neurotransmitters in them. That data is the sort of thing that neuroscience is now able to collect. It's been done for the fruit fly Drosophila, where there is a complete data set of a fruit fly brain and also one of another half fruit fly brain. There are data sets of cubic millimeters of mouse brain currently, and there's a new project underway to map an entire mouse brain at that resolution, at the resolution where you can see the synapses. But what you have then is you have a 3D object. It's basically just a picture of all those neurons. That's not a running model. What's still missing is the transition from this data that you were able to collect, all these structures that look like something in the brain, to something that actually works like something in the brain. You need to go from structure to function. You need real models that you can run. To get to models that you can run, you need to be able to identify what these neurons are and how they work. You need to be able to pull out parameters that will run in a model, and you need to be able to validate that the things that you just designed, what you pulled out of that data, is correct. And that's where you run into a problem. Right now, nobody knows what's in a brain, even a fruit fly brain. If you try to design a solution for the fruit fly brain by saying, okay, we see all these structures, I'm going to map these to some functional models. How do you know that what you did is correct? If everything works, yes, then you have a model that you could put into a little robot body and you'd have a fruit fly flying around and behaving like a fruit fly. That would be great evidence. So the behavioral test at the output, great. But mostly what happens when you model something is you press run and nothing happens. And you don't know where the bug is. Or something doesn't behave well at all. It looks like it has an epileptic seizure and it's just sitting there buzzing around but not doing anything. So how do you know what to do this translation from structure to function correctly? Well, you need brains that we do understand. You need something where we do know everything about it so that you can tell whether the model that you built from that structure you're looking at, whether it's correct. You need ground truth models. You need brains that you can study, that you understand. So this whole brain emulation challenge that we're building is where we have two different ways of making ground truth brains. So ground truth, fully known microbrains, little tiny brains that we can give to someone to say, here, use the best method that you can come up with, and also to us, of course, the best methods that we can come up with to try to reconstruct, to take the data that you can collect from a brain and reconstruct it in a model, and then we can tell you exactly how well you did. We can tell you where you made mistakes, which functions you captured that were in there, which ones you didn't capture, which ones you confabulated that you made up that aren't actually there. And then by knowing which mistakes you made and how well you performed on this, you can get better. So this is very similar to, for example, the challenges that existed in AI, like ImageNet, where you have known images, you know if there's a bicycle or a car that's being occluded by a tree or something, and you use that to train your networks, and you know how well it did. You can improve performance of your model because you know how well it did. So this is the same thing we're trying to do by providing in silico systems, so systems where we design them in the computer that are like tiny brains, and we know everything about them, and we give people the data that they would normally collect. So we give them electron microscopy data, virtual electron microscopy data, virtual calcium imaging, virtual electrode recordings. They take that data and they apply their best methods to it to produce a brain and say, this is what we got. And maybe it's not a whole brain, maybe it's just a piece of neural circuitry of some size, maybe it's a retina or something like that. They give that back to us, and we can tell them how well they did. If they do very well on the in silico challenge, and the in silico challenge has many stages, from extremely simple to very sophisticated. If they get to the sophisticated level and their method is still doing very well, then we put them on the in vitro challenge. That's the challenge where we have our cells that have been cultured on top of electrode arrays. You can look at them, so you can see all the structure, you can see which neurons are connected with which other neurons using a microscope, and you can record from all of them and stimulate them with electrodes. So we know everything about it. It's a ground truth network. And again, the same thing. We give them the data, you give us back what you did, and so forth. So this idea here is exactly the same as with challenges that existed in AI. And we hope to both provide that challenge and also to be our own contestants. I mean, we'll spin it off to a neutral third party to do the challenge, and then we'll be doing this stepwise improvement of our methods as we learn how to translate from structure to function. I think that the value in this, the reason why it's important to have this, is not just because it's the only way for neuroscientists to test their methods. It's not just that it's the only way for them to know if they're making progress, but it's also that as we accelerate the progress that way, in the same way that progress accelerated by having challenges in AI, as we accelerate the progress, and it's, for example, makes it much easier to have machine learning methods that help neuroscientists do this translation, we will discover things about the circuits in the brain, especially circuits that span multiple brain regions, that contain exactly those things we talked about before, these crucial things about how to set up cognitive functions that maybe we don't quite know how to do yet, that we'll discover there. So that will feed right back into AI development, and you have a loop between helping AI develop, helping neuroscience move forward. So we're really trying to close that loop there.